So let us define what is differential entropy. Differential entropy of a function whose probability density function is fx of x is given by h of x is equal to minus infinity to infinity fx of x log to the base 2 1 by fx of x dx. Differential entropy is an important concept in our study of random variables. There is a very common question that comes up in your exams. Derive the equation for the differential entropy of a Gaussian random variable. We know that the probability density function of a Gaussian random variable is 1 by root 2 pi sigma x e raised to minus x minus mu by 2 sigma x minus mu the whole square by 2 sigma x square, where mu is the mean of the Gaussian random variable and sigma x is the variance. We know that differential entropy is defined as h of x is equal to minus infinity to infinity fx of x log to the base 2 1 by fx of x dx. For fx of x, that is the probability density function, if you substitute the Gaussian random variable, we will get hx of x to be equal to minus infinity to infinity fx of x log to the base 2 e raised to 1 by log 2 pi sigma square plus x minus mu the whole square by 2 sigma square dx. So I believe that you can understand how we have derived the differential entropy of a Gaussian random variable. Of course, the steps in this, how we got this, is not explained in detail. That you can do it by yourself. Maybe in the next slide I'll give you an introduction to how it has been derived. Okay. On substitution of the Gaussian random variable in the definition of differential entropy, we get that h of x. And on integration and solving this, we'll get the differential entropy of a Gaussian random variable to be equal to 1 by 2 log 2 pi sigma square e. You can note that the differential entropy of the Gaussian random variable has nothing to do with its mean and depends only on its variance. The differential entropy of a Gaussian random variable, derive the equation for the differential entropy of a Gaussian random variable, is an highly expected question in your exams. I want you to integrate and solve it. Now I've given you all the steps and I've given you the answers. The significance of this derivation is that we come into a conclusion that the differential entropy of a Gaussian random variable does not depend upon its mean. Next important concept that we are going to study is about what is meant by mutual information. What is meant by mutual information? The mutual information, or MI, of two random variables x and y is a measure of the mutual dependence between the two variables and is defined as I x semicolon y is equal to minus infinity to infinity integral double integral minus infinity to infinity f of xy comma xy is a two variable log to the base 2 conditional probability of fx on the condition that y has already occurred by fx of x dx dy. So what we mean by mutual information is that how far the random variable x depends upon y, or what is the percentage or the level of dependence. Mathematically, we can express this using this equation, and you may need to calculate mutual information of two random variables. So mutual information of two random variables I x colon y is given by log p probability of xi when yi has already occurred, conditional probability of xi with respect to yi divided by probability of xi. So when you expand this, we'll come into a conclusion that mutual information of x upon y is the same as mutual information of y upon x. Mutual information of x on y will be equal to mutual information of y on x. There might be questions in the exams asking you to prove this. Prove that mutual information of x on y is same as y on x. So let us do a problem. Now we'll be doing some problems. In the second module, we'll practice a few problems. We have a source A1 to A6 and we have the probabilities, corresponding probabilities. You are asked to find the entropy of the source. Okay. And then you are asked to compare the entropy with the entropy of a uniformly distributed source with the same alphabets. See, what I am discussing here are previous year question papers. If you are not attentive, you cannot make up with the exams coming up. So listen here, how are we going to solve the problem? Entropy is defined as h of x is equal to sigma I is equal to 1 to n. Here n is 6, no? 6. Then what happens? What is that? P x into log P of x. So you can do it, right? Probability P of x is given. The alphabets are given. So for this example, here we can take this. This is the equation. So on substituting the respective probabilities, what you will get? 0.1 into log to the base 2, 0.1, 0.2 log to the base 2, 0.2 log 3. So you get that to be 2.4087 bits per symbol. If the source symbols are equiprobable, then P of I is equal to 1 by 6. This is the second condition, that when the probabilities are uniformly distributed. For the first thing, first part of your question is to find out the entropy. Entropy is given to be Pi log 2 to the base Pi. So let us consider a situation where Pi is 1 by 6, it is uniformly distributed. So as it is, we are finding out the uniformly distributed condition. In that case, what we'll get? 2.5850. So the original entropy is less when compared to the uniformly distributed one. Am I right? Yes or no? So let's do the next problem. X be a geometrically distributed random variable. P of x is equal to k is equal to p 1 minus p raised to k minus 1. Okay, find the entropy of x. Suppose if x is greater than k, where k is any other positive integer, what would be the entropy of x? Substituting on the equation for entropy with the probability distribution function and expanding, you will get h of x is equal to log to the base 2p minus 1 minus p by p log to the base 1 minus p. So what we are going to do is that we are going to solve for p of x is equal to k on the condition that the random variable x is greater than k. Okay, presuming that k is less than or equal to capital K. So in that case, probability of x is equal to k. So in that case, we get p of 1 minus p raised to k minus 1 by probability of x, random variable, that is greater than k. So we are going to find this. This is equal to sigma k is equal to k plus 1 to infinity p of 1 minus p raised to k minus 1. On solving this, you will get p of x is equal to k when the random variable x is expected to be greater than k to be equal to 1 minus p into 1 minus p raised to k minus 1 by 1 minus p raised to k. Now, see, this is a 14-mark question in your exam. So we get the probability p of x is equal to k when x is greater than k, that is equal to p 1 minus p raised to k, 1 minus p raised to L minus 1, where L is 1, 2, 3, and so on. Okay. So is geometrically distributed as given in the question. So using the results, what we'll get? The entropy of X on the condition that X is greater than K, we'll get it as minus log 2 P 1 minus P by P log 2 to the base 1 minus P. So thank you all. Thank you very much. The next class we'll be seeing more problems.